Hey guys, let's take a look at this practice final here. And of course, don't forget to put your name on the top, right? And let's jump right into number one here. We've got, hopefully you recognize this is an angle bisector. And when we draw an angle bisector and we extend it to the opposite side of the triangle, it cuts the opposite side into proportional parts. This part is 2. If the whole side is 6, then this remaining part must be 4. And that allows us to set up this proportion. 2 over x should equal 4 over 10. Okay, my cross products are 4x equals 2 times 10 is 20. And we get x equals 5. Good. Similar problem right here. Angle bisector, cutting the opposite side into proportional parts. If the whole side is 30, and this is 12, and this guy is 18. And that gives us a proportion 18 over 21. That over that should equal 12 over x plus 9. Okay, so we get 12 times 21. What's that? I should know that off the top of my head. I don't. 252 equals 18 times x plus 9. Don't forget to distribute here. 252 equals 18x plus 162, right? It's 9 times 9 plus 9 times 9. And we'll subtract 162 from both sides, and I believe we get 90 equals 18x. And if we divide both sides by 18, that's weird, we're going to get x equals 5 again. Okay. All right, another one. Similar idea here. This side, if the whole side's 18x plus 5 and this segment's 25, then this guy is 18x plus 5 minus 25, which would be 18x minus 20. Good. And then you can set up your proportion here. 25 over 35 should equal 18x minus 20 over 98. Good. We'll cross multiply, and we're going to get 2,500 less 50. So we're going to get 2,450 there, right? Equals 35 times 18x minus 20. And let's distribute that. 35 times 18, we get 2,450 equals 630x minus 35 times 20 is 700, right? So we'll add 700 to both sides. And we're going to get 2,450 plus 700 gives us 3,150. Don't need to type that in, I guess. And I will probably have to type this in. No, not really. I think we're going to get x equals, maybe we'll do it, 3,150 divided by 630. And now it's going to come out to a nice whole number. It's 5 again. I knew it. Okay. Well, that's weird. Hopefully you didn't get all those and think that you were doing it wrong. Last one here on this page. What have we got? If this segment's 4, that's 2, and that's 7. Now this time we have parallel lines, and we know that parallel lines essentially create similar triangles. So these sides will be proportional to one another. 4 over 2 should equal this side over 7. But what is this side? The whole thing is 6 plus 3x. Then this is 6 plus 3x minus 4. So it's 2 plus 3x, or 3x plus 2. I like to put the variable first. So that should equal 3x plus 2 over 7. Good. And of course, if you forget, you should be able to remember that you have similar triangles because these are corresponding angles. When the lines are parallel, they're congruent, and these are corresponding angles. When the lines are parallel, they're congruent. So you have angle-angle similarity. 7 times 4 is 28 equals 2 times 3x is 6x plus 4. Good, we'll subtract 4 from both sides. We get 24 equals 6x. This time x equals 4. Good, let's see what's on the next page. All right, here they want us to find the missing lengths. We've got special triangles. Hopefully you recognize them. We've got a 30, 60, 90 triangle and a 45, 45, 90 triangle. Of course, if you look at this one, there's clearly not enough information, so we know we have to start in this triangle. And this is the short leg. This is the long leg. I know that because the long leg will be across from the 60-degree angle. The short leg will be across from the 30-degree angle. And I know that the short leg equals the short leg times the square root of 3 equals the long leg. Short leg times the square root of 3 equals the long leg, 12 square roots of 10, right? So I will divide both sides by the square root of 3. I'm going to get S equals, what do we get there? 12 times square root of 10 divided by the square root of 3. And we get 4 square roots of 30. Okay. And by the way, if you forgot that rule, hopefully you remember, because it's fairly easy to rederive, that the short leg times the square root of 3 is the long leg, and the hypotenuse is 2 times the short leg. You can either draw yourself an equilateral triangle and rederive it, or you can say, I know the tangent of 60 degrees. You could do this as well. Tangent of 60 degrees equals opposite over adjacent, 12 square roots of 10 over S. And you can solve it that way. It's another way to skin the cat. Okay, so now I know this side here is the hypotenuse in this triangle, which equals 2S. And 2S is going to be 8 square roots of 30. Now when we look at the 45, 45, 90 triangle, this is the short leg. Or I should say just the leg, because both the legs are the same in the 45, 45, 90 triangle. And we know the hypotenuse equals x equals the leg times the square root of 2, right? And if you forgot it, you could go back to trig. You could say the sine of 45 degrees. You could also say sine of 45 degrees equals opposite over hypotenuse equals 8 square roots of 30 over x. And you could do the numerator shuffle and solve it that way. Either way, you're going to get the same answer. So this is going to give me 8 square roots of 60. Square root of 60, can we clean that up? 8 times square root of 60, which is going to simplify to 16 square roots of 15. Okay, so we found x, okay, but we had to do a couple steps to get there. All right, let's try the same thing on number 6 here. This time we're starting in our 30, 60, 90 triangle, but they give us the hypotenuse. So I can immediately say, the short leg will be half the hypotenuse. This leg here is 6. Good. And now we've worked our way into the 45, 45, 90 triangle. So this side 6, this side 6. And by the way, yeah, you can absolutely go back to Pythagorean theorem if you want to. And you can say 72 equals x squared and take the square root of both sides. And you're going to get the square root of 9 times 8, right, equals x, which will give you, we can do better than that. We could have done, because we're going to get 3 square roots of 4 times 2, right? And we can do better than that. So we get 3 times 2 times the square root of 2 equals x. And we get 6 square roots of 2 equals x. And if you're uncomfortable with that, hopefully you've got one of these calculators that will help you simplify that and confirm that. But the other thing you can do is you can simply say, I know the hypotenuse in this special right triangle equals the leg times the square root of 2. See how quick, if you remember the shortcut, it's wicked fast. All right, let's try number 7 here. Find the value of each trigonometric ratio. We've got cosine, we've got sine. Hopefully you remember. So, ka and toa, right? They want us to find the cosine of x. Cosine equals adjacent over hypotenuse. So for this angle x, cosine of x equals adjacent. The adjacent side is the side that's closest to the angle that is not the hypotenuse. So it's going to be 40 over the hypotenuse. Always the longest side is 41. Good. Could we do the same thing for the sine of x in this triangle? Remember, sine is opposite over hypotenuse. So the sine of x equals, if I'm looking at x, the opposite side is all the way across the triangle. 36 over our hypotenuse is 39. And if you want to simplify that, you can divide top and bottom by 3 and get 12/13. Good. Let's see what's on the next page. Okay, here they want us to find the cosine of z. Again, so, ka, toa, right? Hopefully you can see that. You can see that? Good. All right. So the cosine of angle z here is going to be adjacent over hypotenuse. I'm looking at angle Z. The adjacent side is 30. And the hypotenuse is the longest side, 50, which conveniently simplifies to 3/5. Good. Over here, they want the tangent of angle Z. Remember, tangent is TOA, opposite over adjacent. So I'm looking at angle Z. The opposite side is 40. Over the adjacent side is 9. 40 over 9. Okay, and we can't simplify that any further. So, good. All right, could we find the value of each trigonometric ratio to the nearest 10,000th? Okay, good question. So you can just go to your calculator and you can say tangent of 39, and we're going to round that to the nearest 0.10th, 100th, 1000th, 10,000th. I'm going to round 7, 8 up to 8. Okay, that would be to the nearest 10,000th. Okay, we can do the same thing for the tangent of 34 degrees. Okay, we're going to round this to the nearest 10,000th. There's the tenths, hundredths, thousandths, and 10,000ths. We'll round to 5 in the 10,000ths place. Good. It's on the next page. Okay, here they want us to find the measure of the indicated angle to the nearest degree. How are we going to do that? Well, you might recognize that this is an isosceles right triangle. And you just say, well, that's 45 degrees. If you recognize your shortcuts. If not, you could say, I could say the tangent of this angle x equals opposite over adjacent, 6 over 6, right? And then I can say, well, okay, so x is an angle whose tangent is 6 over 6 is 1. What angle has a tangent of 1? Second function tangent 1, and your calculator will tell you that is a 45-degree angle. Good. Here, this one's a little trickier. They want us to find this angle. With respect to this angle, what sides do I know? I know the opposite, and I know the hypotenuse. So, ka and toa. Which trig function correlates opposite and hypotenuse? Opposite and hypotenuse, that's sine. So the sine of my angle x equals 13 over 35. Opposite over hypotenuse. Good. So I can use the inverse trig function then to figure out what angle that is. What angle has a sine of 13/35? X is an angle whose sine is 13/35. Let's punch that in. And we get x equals to the nearest degree. We're going to call that 22 degrees. Good. Could we find each angle measure here to the nearest degree? If the cosine of y is 0.4695, what would the measure of that angle be? Okay, so basically what we're going to say is y equals, or the measure of angle y is the inverse cosine of that value. What we're saying is y is an angle whose cosine is 0.4695. 0.4695. And we get to the nearest degree, 62 degrees, pretty close. Good. Same thing over here. If the tangent of angle V is 0.3640, then the measure of angle V is the inverse tangent of 0.3640. Basically asking myself, what angle has a tangent of 0.3640? If we kind of reverse look up in our table, which is really what the calculator is doing, we can figure out what that angle is, 0.3640, using that inverse tangent. Good, and we get the measure of angle V equals 20 degrees. Good. What's on the next page? Okay, here they want us to find the missing side, round to the nearest tenth. I'm going to put SOHCAHTOA back up here. Okay, it's good to remember, because to find the missing side, you can see we don't have enough information to use Pythagorean theorem. We don't have 2 of the 3 sides. So we've got to use our trig ratios. We know this angle is 65 degrees. With respect to this angle, I'm looking for the opposite side, and I know the hypotenuse. Which trig function correlates opposite and hypotenuse? That's sine. So the sine of 65 degrees equals opposite over hypotenuse, x over 20. Good, I can multiply both sides by 20 here and get, I can just punch it in my calculator now. 20 times sine 65. And I get 18 to the nearest tenth, 18.1 equals x. Good. Let's do the same thing over here. I've got this 22-degree angle. With respect to that angle, I'm looking to find the opposite side, and I know the hypotenuse. Again, opposite and hypotenuse, we're going to use sine. Sine of 22 degrees equals opposite over hypotenuse, x over 33. We'll multiply both sides by 33. 33 to get 33 times sine 22. And I get 12.4 equals x rounded to the nearest tenth. Good. All right, here they want us to find the area of each triangle. We're going to need the base and the height, right? Unless you remember that shortcut, area equals 1/2 AB sine C, right? Remember that one? You could do that. Could we do that here? Area equals, if we take this sine of this angle, 1/2 AB sine C. I don't know both those sides, so we're going to have to work through this a little bit. Good. Let's see where we can go. It's going to have to start in this triangle because this is the only place where we actually know a side, right? And if that angle is 48 degrees, this angle is 42 degrees. And I think from this we could find the height, which will be very helpful. Okay, so we could say, if we're looking at this 42-degree angle, height is the opposite side and 30 is the hypotenuse. So the sine of 42 degrees equals h over 30. Good. Let's multiply both sides by 30 to find that h. We get 30 times sine of 42. So I get 20.07 equals h. Round intermediate values to the nearest tenth. Use the rounded values to calculate the next value. Round your final answer to the nearest tenth. Okay, so we're going to round our intermediate values to the nearest tenth. This will be 20.1. Okay. All right, so if our height is 20.1, I just need the base now. How are we going to find the base? We could use Pythagorean theorem to find this piece here, right? We could say, let's call it x, and we could say x squared plus 20.1 squared equals 30 squared, right? And that guy's 900. 20.1 squared gives us 404.01. Okay, let's go ahead and subtract that from both sides. And we're going to get x squared equals 900 minus that answer gives us 495.99. How do we solve for x there? Swish and flick, right? We get x equals 22.3. I kind of wish we were doing these intermediate values to the hundredths because we do accumulate a bit of error here as we keep rounding, the more steps you have. But that's okay. We'll deal with it. All right, what's this little piece here? Well, here I could say, why don't we use a trig function here? Since I don't know the hypotenuse of this triangle, I can't use Pythagorean theorem over here. But I could say, with respect to the 70-degree angle, I know the opposite and I'm looking for the adjacent. Let's call it A. So katoa, right? Does tangent correlate opposite and adjacent? Yeah. So let's say the tangent of 70 degrees equals 20.1 over A. Good. And here we could do our numerator shuffle, couldn't we? We'll bring this guy over here, 20.1. And that'll go away, and we're going to get 20.1 divided by the tangent of 70. So we get A equals 7.3. Okay. All right. Now, after all that, we have a triangle that was what we were looking for in the beginning, where the height is 20.1, and the base is the sum of these two, 7.3 plus 22.3, 29.6. And I can say area equals 1/2 times base times height, right? Which is 1/2 times 20.1. I got those backwards. 29.6 times 20.1. Fortunately, multiplication is commutative. 0.5 times 29.6 times 20.1. And we get an area of 297 we'll round it 5. Okay, if you're even in the ballpark on that, you're good depending on how many steps you took. If you were rounding your intermediate values to the nearest tenth, you might be plus or minus that. But those, and they didn't give us units, so that would be just units squared. Good. Let's see if we can do the same thing on 20. On 20, let's try a little shortcut. Let's try our 1/2 AB sine C shortcut. I don't know if you remember this, but let's just call this side A, or angle ABC, which makes this side A. This is side B, and this guy over here is side C. And yeah, I don't know if you remember, but back in chapter 8, we proved that area of a triangle equals 1/2 side A times side B times the sine of angle C. So this could eliminate one step for us if we do this. We still have to find the height in order to work our way from this triangle into this triangle to find side A. So let's go ahead and do that. We've got, oh, maybe we don't have to do that. Maybe we could use law of sines here. Let's try this. In this triangle, if this is 57 degrees, then this guy here is 33 degrees. And in this is also a right triangle. If this guy's 41, then this guy over here is 49 degrees. And now all of a sudden I might be able to say, I could find side A by saying the sine of 49 over side B over 18 equals the sine of 33 over side A. Good, and we can solve for side A. This is going to save a step. A times the sine of 49 is 1 cross product equals 18 times the sine of 33. That's our other cross product. And we'll divide both sides by sine of 49. And this is that case where you can punch it right in your calculator because it's all neatly solved for A. 18 times sine of 33. Don't forget to close those parentheses there so we don't accidentally divide a 33-degree angle by this. Sine of 49. Divide by sine of 49. And we get A equals 12.98. That's going to round up to 13.0 according to what they want us to do. Good. All right, if this is 13.0, we can now go ahead and plug that into our formula here. We get A equals 1/2 times AB 13 times 18 times the sine of angle C is the sum of these two angles. That's 57 plus 41, 98 degrees. Good, let's try this. Area equals 0.5 times 13 times 18 times the sine of 98. And we get the area is 115.9 units squared. And yes, that's the same answer we would have gotten if we had paused, found the height, and then found this segment and this segment to add them together to get the base. So we saved ourselves a little bit of work there. Circles. This is the most recent unit we covered, so hopefully this stuff was fresh in your minds when you encountered this. We've got 18.1 here, that's a radius, and they want us to find this segment X, and this segment's 15.3. And this guy here is connecting the center to the edge of the circle. It's got to be another radius. And when a chord is perpendicular to a radius or a diameter, we know it gets bisected. And therefore, if that segment's 15.3, then this segment is 15.3. Good. And this segment is X. What's this segment here? Well, it would be, if the radius is 18.1, then this guy's 18.1 minus X, right? Now we know that when two chords intersect inside the circle, the products of their segments are equal. The problem is this is not a chord, this is a radius. But if we extend it to the other side of the circle, ta-da, we have a type of a chord called the diameter, right? And so this segment's 18.1. So now what I really want to know is what's this whole segment right here? 18.1 plus 18.1 minus x. That sounds like 36.2 minus x. Good. Now I know the products of the segments are going to be equal. This times this, 15.3 times 15.3 is going to equal x times 36.2 minus x. Okay, let's go ahead and crank this out. 15.3 squared. We get 234.09 equals, let's distribute that x, 36.2x minus x squared. Good. All right, how are we going to solve this now? Without whole numbers here, you know you're going to go straight to the quadratic equation. So we're going to subtract 234.09 from both sides. 4.09. We're going to get 0 equals, I'm going to just rearrange it so it's in standard form. Negative x squared plus 36.2x minus 234.09. Okay, so I know A equals -1. B equals 36.2. C equals -234.09. And we can plug this into our quadratic formula. X equals -b, -36.2, plus or minus the square root of b squared, 36.2 squared, minus 4 times a, -1, times c, -234.09, all over 2 times a, which is going to be -2. Okay? All right, so let's clean that up. I'm going to just tackle this centerpiece here and say 36.2 squared minus 4 times -1 times -234.09. So I'm going to get x equals -36.2 plus or minus square root of 374.08 all over -2. I'm going to take the square root of that, well, I got it in my calculator, and I get -36.2 plus or minus 19.34 all over -2. Okay, and now got to be careful here because it turns out that both roots are positive. It looks like both roots are positive. I'll show you. -36.2 plus 19.34 over -2, and -36.2 minus 19.34 all over -2. So here we get -36.2 plus 19.34 divided by -2. That gives me a positive 8.43. Okay, but I believe this is also going to be a positive root. So basically what it's saying is there are 2 different circles in which this could happen, or there are 2 different values of x for which this could happen, and we'll see if we can figure out what that means when we're done here. -36.2 minus 19.34. We're going to divide by -2, and here we get 27.77. Okay, all right, so what that's saying is you could have a circle with a radius of 18.1 where x is 8.43 and satisfy this condition. You could also have a circle where x was 27.77. Okay. Here's the problem. Is that going to make sense? What could we, if x was 27.77, it'd be longer than the radius, and it would be over here. So let's just take a look at this. 36.2 minus 27.77 gives us 8.43. So what the algebra is telling you is you could have this circle, or you could have a circle with the chord over here and x over here. It's really giving you the same answer twice. In this particular case, we're going to say that x is 8.43 because it makes more sense with the diagram that they gave us than saying that x could be 27.77 and have the chord all the way over there. All right, tough problem. If you struggled with that one, don't fret. That was a good one to get you guys set up for Algebra 2. All right, let's see if we can do the same thing with 22 here. Similar problem. They want us to find x. This segment's 8.8. We know that these are going to be congruent because we have a chord that intersects a radius at a right angle, so it must be bisected. And then this 22.4 refers to the diameter. So if I were to extend this across, this would be 22.4. That's x. Then this segment here is 22.4 minus x. Good. All right, you can see where we're headed with this, hopefully. The product of the segments is going to have to be the same. 8.8 squared is going to have to equal x times this quantity, 22.4 minus x. Good. And 8.8 squared gives us 77.44 equals 22.4x minus x squared. Good. Let's put that in standard form. We're going to subtract 77.44 from both sides. Okay, I'm going to get 0 equals, I'm going to rearrange, negative x squared plus 22.4x minus 77.44. Okay, so we get a equals -1, b equals 22.4, and c equals negative 77.44. Yes, for those of you who have programmable calculators going into Algebra 2 and Pre-Calc next year, make sure you program into your calculator the quadratic formula. It is going to save you all of this work. Once you know what it is, let the calculator do the heavy lifting for you. Okay, once you know what it is and how to use it. So we're going to get x equals negative b, negative 22.4, plus or minus the square root of b squared, 22.4 squared, minus 4 times a times c, all over 2a, which is going to be -2. Good. Let's see if we can clean this up. I'm going to go under the radical. I'm going to go for the discriminant first. 22.4 squared minus 4 times -1 times negative 77.44, 192. And I'm going to take the square root of that, and we're going to get negative 22.4 plus or minus 8 square roots of 3. I'm going to go ahead and turn that into a decimal. 13.86 all over -2. So I get negative 22.4 minus 13.86 divided by -2. So we could get 18.13 for a value. We could also get negative 22.4 plus 13.86 divided by -2. Could also be 4.27. Okay, now which one makes sense in the context of this sketch? It's going to be the 4.27, okay? Because if I was at 18.13, the radius of this is 11.2. So I've already gone past the center of the circle, and I'm talking about an identical chord mirrored across the circle over there like that. And we solve for this other segment when we're talking about the 18.13, okay? All right, again, don't fret if you guys struggle with those problems. Those are toughies. And but get used to seeing things like that and bringing your Algebra 1 back into it and your quadratic formula, because you're going to see a lot of them next year. Here, could we find the area of each sector? First question, can you find the area of that circle, right? I tell you, there's not much to memorize in math, but one of the things I do tell you to remember is circumference and area of a circle. Area of a circle equals pi r squared. Okay, so we could find the area of the entire circle, couldn't we? And if we could find the area of the entire circle, could we find the area of a fraction of that circle? Yes, we could. And we are looking at a fraction, of this circle. If you want, you could say area equals pi times 15 squared, or 225 pi, right? But I don't have a full circle. I have what fraction of that? I could say that I've got 30 360ths of a circle. How do I know I have 30 360ths? I have this sector that's 30 degrees. A full circle would be 360 degrees. You could simplify this to 336. You could even further simplify it to 1/12. That's 1/12 of a circle times 225 pi. Okay? And so 225 divided by 12. So I get 18.75 pi meters squared. Okay? If they don't tell me to round to a certain amount, then I'm assuming they want an exact value, and I'm going to leave it in terms of pi. Remember, pi's dessert. Leave it for last. If you wanted to turn it into, I don't know what they did in the answer key. If you want to turn it into a decimal, well, multiply it by pi, and you get, that is approximately 58.9 meters squared. Good. Can we do the same thing here? This one was a little easier. Probably should have done this one first. Do we know the area of this circle? It's pi times r squared times 9 squared. So this is 81 pi. But I don't have a full circle, do I? What fraction of a full circle do I have? It's just like you had some really hungry people over for Thanksgiving and they didn't want to share and they wanted a quarter of the entire pie, right? That's a quarter of a pi. So 1/4 times 81 pi is 81 pi over 4. 81 pi over 4 meters squared. Now, if you need to turn it into a rounded value, 81 divided by 4 times pi, that is approximately 63.6 meters squared. Good. Okay, 25 here. We've got a quadrilateral inscribed in a circle. And hopefully one of the things you remember is that the opposite angles in an inscribed quadrilateral are supplementary. They're going to add up to 180. How do we know that? Well, you could think of this as an inscribed angle intercepting this arc. In this as an inscribed angle intercepting that arc. And those two arcs add up to 360. And we know inscribed angles equal half the measure of the arcs they intercept. So together they have to add up to half of 360, which is 180. So I could say 6x plus 10 plus 6y minus 4 equals 180, right? I could also say 6y plus 2. I'll do the x's first so we can do some systems of equations operations on this. 7x minus 10 plus 6y plus 2 is also going to equal 180. Okay, can we clean this up a little bit? I'm going to just take both of these equations and just simplify them. This becomes 6x plus 6y. And I got positive 10 and negative 4. That's positive 6. And I'm going to subtract that 6 from both sides and get 174. I skipped a step there. I'm hoping you guys are comfortable with that. Let's do the same thing here. I get 7x plus 6y. And now my non-variable terms, I've got negative 10 and positive 2. That gives me negative 8. To get rid of that on this side, I'll add 8 to both sides. Okay? So I get 188. Okay. Now, one of my favorite things from Algebra 1 is solving systems of equations using elimination. Few things in algebra are as satisfying as elimination because all you have to do here is subtract one of these equations from the other in order to get one of the variables to drop out. Which variable goes away? The y's. The y's are going to go away. 6x minus 7x leaves me with negative x. 6y minus 6y. Don't forget you're subtracting this entire equation. Sometimes it helps to put it in parentheses. 6y minus 6y is 0. Eliminated. And 174 minus 188 leaves me with negative 14, right? If negative x equals negative 14, then positive x equals positive 14. And now how do I find y? I can go and plug it back into one of these equations. And I can say 6 times 14, plus 6y equals 174. And 6 times 14 is going to be, let's see, 84, is that right? So we'll subtract 84 from both sides. I'm trying to save some paper here. I get 6y equals 174 minus 84 is 90. Divide both sides by 6. And I think we get y equals 15. Good. Let's try another one. Here, again, same idea. We know the opposite angles are going to be supplementary because this is an inscribed quadrilateral. So I could say 11x plus 6 plus 15y minus 4 is going to equal 180. Okay, these opposite angles. And I could say these angles also, 9x plus 9 plus 15y plus 9 is going to equal 180. Good, let's simplify these. I'll just bring both of these guys down here. I get 11x plus 15y. I get 6 minus 4 gives me 2. I want to get rid of that 2, so I'll subtract 2 from both sides. So that's 178. Good. Over here, I've got 9, and 9 is 18, and I want to get rid of that 18, so I'm going to subtract it from both sides. So I get 9x plus 15y equals 162. Okay. I can subtract one equation from the other to get the y's eliminated, right? So 11x minus 9x gives me 2x. 15y minus 15y gives me 0. 178 minus 162 gives me 16. And it looks like we're going to get x equals 8. Good. I can plug that back in to find y. Why don't we find y right here? 9 times 8, right? That's going to give me 72 plus 15y equals 162. We'll subtract 72 from both sides, and I get 15y equals 90. Gee, this program that I use to generate these problems almost looks like it has some patterns. Definitely some patterns. 90 divided by 15 gives me 6. Good. All right. Okay. All right, let's take a look at 27. Here they want us to solve for x and assume that lines which appear to be tangent are tangent. So that tells me whenever I see a tangent, I just want to go ahead and mark that 90-degree angle because that's valuable information. And as soon as I have that, if I know this is a tangent, I know it intersects a radius at a right angle, and now I have a right triangle, and now I've got Pythagorean theorem all over the place, right? So I could say that x squared plus 9 squared equals, how long is the hypotenuse? X plus 5, good, equals x plus 5 squared. Now be careful, don't fall for the classic blunder. X plus 5 squared is not x squared plus 25, right? You got to FOIL that out. So we get x squared plus 81 equals, I still do this. I still do this so that I don't fall victim to the classic blunder. Write out the two binomials, right? And we'll say x squared plus 81 equals x squared. X times x is x squared. X times 5 is 5x. 5 times x gives me another 5x. And 5 times 5 gives me 25. Boss level distribution, right? The x squareds will really nicely just drop off, right? You could subtract x squared from both sides. I get 81 equals 10x when we combine our like terms, plus 25. We'll subtract 25 from both sides. And I get 56 equals 10x. And I believe we're going to find that x equals 5.6.